Now, if you did the Lewis dot, who did I steal this from? Trin, you again? Thank you. If you did the Lewis dot, we would be on high alert, and I'm going to assume everybody could get to this point. Because what we would find, we know we have to share how many?
At least 10.
At least 10. And so we would run through it, and we have to share our 10, and then we would find there were leftovers, and the leftovers, of course, go to the central atom. So I'm going to assume everybody could go here to here. Now, let's fill this out. Okay, let's answer our questions here. Marco, how many atoms?
5.
Okay, there are 5 atoms. Then tell you how many lone pairs?
1.
1. So our number of things here, Timothy?
6.
6. So our orientation here, Eddie? Eddie? Yeah.
Is it
Octahedron.
boron or bromine?
Oh, wait a minute.
BR?
BR. Oh, yes. Pardon me. What is that? If you're keeping score, that's 3. I'm reading a book by John Medina. He's a neuroscientist. And what causes you to really foul up? Well, stress is one, but 2, lack of sleep is the second thing. I mean, he's got a separate chapter of what lack of sleep does to the brain, bad things. And what does stress do to the brain, bad things. So anyway, you can see you have ample evidence of that right here. Okay, now, yes, that is a VR. Thank you. Molecular shape, well, let me draw my generic octahedron. And I will use BR this time. Remember, we just had a little discussion. Every spot is identical in an octahedron, so it doesn't matter where we put the lone pairs. I'm just going to stick them down here. And we'll have F, 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 F. And if you're talking about structures, that is a Lewis dot structure. This is a VSEPR structure. And the difference is with VSEPR that this major theory we've been using, when you're using this table, this is the theory you're using, valence shell electron pair repulsion theory. That's the CAT repulsion theory. Okay, I'm going to put it down there, and let's look at a structure. Does somebody have one? Ah, beautiful, Meredith. Okay, I put the lone pair down here. Now, we pretend we can't see the lone pair when we start talking about molecular shape. So, with a little imagination, what do we see left?
Square pyramid.
Square pyramid. Perfect. Now, notice something. I'm going to exchange the red. I'm going to put it in what was the plane here. Turn it, you see the same thing. And so that should convince you, no matter where you put it.
But that's only for certain shapes, right? For certain,
Yes, yes. Okay, square pyramid. Now, we just have the one lone pair, so yeah, we're going to be squeezed. So Meredith, what angles do you see remaining when you think?
90.
What's that?
Less than 90.
Less than 90? Do we have any others still hanging around?
Oh, yes, less than 20.
Less than 180. And when I use this, I mean less than, not angle, because they use that for both. Now, what about the polarity here, Tanya? What would you say? But you've got huge force. Yes, polar. When you have lone pairs, you can almost always bank it's going to be polar. We only have 2 cases where it's not.
That's when they cancel out.
When they cancel out. Like that case we just saw, that bottom structure right down there. Okay, then how about resonance forms? None. If we look over here, if you look at the top structure, this is really what we're looking at. And this is a wonderful table because as you study, over here on the side, I know it's probably hard to see because it's so tiny, but they give you some examples of other molecules that will be like that. So it would be great to take some of those for practice and see then if you come up with that or not. Okay, then let's do our last one. If we did XeF4, as our central atom, and so it could violate. And we know it's going to share at least how many? 8. Well, if you go through that process, what you would find, here's your 4 fluorines around it. And then there were leftovers. When you think of the available, and there are 4 leftovers, and that's going to be 2 lone pairs. So I'm going to assume everybody can go to here to here, because you've had so much experience with Lab 15. So let's fire through and see how we come up with that structure. So let's think number of atoms. Charles, how many atoms? 4. Allison, how many lone pairs? 2. Antonio, how many things? 6. So, Eddie, what's our orientation?
Octahedron.
Octahedron, good. Now, here's an issue. Before I said it didn't matter where you put the lone pairs. Let me borrow yours again. When we come up with 2 lone pairs, now in the previous one where we had just 1 lone pair in an octahedron, didn't matter where we put it. Now it becomes real important because once you put your first one on, a lone pair does not have another nucleus to help control it or attract it. So it's big and bulky, and the most repulsion of all comes from a lone pair. So you can imagine lone pair to lone pair, that's like 2 tomcats in the same neighborhood. You want to get them as far away from each other as possible. And to do that, we'll put them across from each other. Because if they're across from each other, the angle is what? 180, whereas 90, and that is bad news, because we know anything less than 100 degrees is like your mother-in-law living on the same block. It's crowded. Okay, so when you have a second one, put it across. Okay, so here's our shape, our orientation, but then when we talk about molecular shape, you take these off, what do you see? Square planar. Okay, now think of all these weird words. We have trigonal planar, trigonal pyramid, trigonal bipyramid. We have, let's see, square pyramid, we have square planar. If you just try to memorize those, you will go nuts. What you got to think when you hear the words square planar, analyze, translate. Square, 1, 2, 3, 4, makes a square. Planar means flat. Square pyramid would be pumped up in the middle. Okay, so square planar. Okay, now, what are our bond angles? And I want you to think, is it right on the money or is it being squeezed? And you can also look at the picture up there. So, Bruce, what do you think?
It's 90 degrees and it's not being squeezed.
Okay, and are there any other angles?
No.
180.
Oh, there is still. Oh, even though you can't see them.
No. Here's what you look like.
Yeah.
Okay, lone pair pushing down.
Yeah.
Lone pair pushing up. That's why we're not squeezed. This is your second weird case. You have lone pairs and you're not being squeezed. There's only 2 cases where that's true. Okay, here's your 180 is still surviving. Here's your 90 is still surviving. Thank you. All right, and how about polarity this one? Non-polar, good. How about resonance forms? 0. Good job. Now, let's go back to here. This is your table 8-3 on page 316. This is a really good table. Let's just run down through it quickly. AB2 with 1 lone pair. Polar or non-polar?
Polar.
Polar. AB3 with 1 lone pair. What's that shape? Molecular shape.
Trigonal pyramid.
Good. Trigonal pyramid. Polar, non-polar?
Polar.
Polar. Okay, AB2 and 2 lone, yeah,
What are the angles?
you tell me.
I think 190.
Those are less than
120.
No, that's not even less than 120.
Oh,
Let's go
less
back
than-
to the
less than
top.
109.
Okay, let's go to the top. Less than
120.
120, because you started as a trigonal planar. Okay, now, what are the angles here? Less than
109.5.
109.5. Okay, now, AB2 with 2 lone pairs, polar or non-polar?
Polar,
Polar, okay, bond angles,
less than 120. Less than 109.
less than 109.5, because think of your basic tetrahedron is 109.5.
It's
Now, let me ask you this, yeah, it's angular or bent. Okay, I've got this and I've got this. Which has the smaller angle? You said less than 109.5 with a little prompting. And you said less than 109.5 with a little prompting. But which is the smaller angle, in here or in here? Case 1 or case 2? Case 2, why, Marco?
Because there's more squeezing because you have two.
2 lone pairs, because you get squeezed by each lone pair and it's additive. Okay, great. Now, what's my shape? Don't pretend you can't read that. Probably most of you can. What's my molecular shape? Seesaw. That's the weird one. Polar, non-polar.
Polar,
Polar. Okay, what's the molecular shape? T-shape. Polar, non-polar.
polar.
Polar. Good. Rick?
I thought the, whatever the
Which-
pairs are
this-
supposed to be far apart from each other.
Okay, they're 120 degrees. That's the problem of drawing it on a flat piece of paper. If you're doing OWL, 8.1, I believe it is, has some fantastic, if you use JMOL and you get these things in 3D and you get to rotate them and you can see them a lot better. I agree. Those look really close together, but that's actually 120. It's as far as if they put them here and here. It's distorted because it's flat. Yeah.
Why wouldn't they put them on the top and the bottom?
Okay, because
I know
if you
said
put
the
one,
plane, but-
okay, let's go back to this. If I put it on the top, the lone pair on the top, it's got 1, 2, 3 neighbors at 90. If I put it in the plane, it's only got 2 neighbors at 90. And having just 2 neighbors crowding you is better than having 3 neighbors crowding you. And we talked about that last time, but I know you hear so much, some of it goes zip in and out. You're overwhelmed by it all. Okay, let's see, we made it down through here, and what was the shape of this one?
Linear.
Linear, polar, non-polar?
Non-polar.
Non-polar, any crowding? No.